Today we're going to look at power in more detail. There's a couple of formulas for power, and we will understand the work-energy theorem as well. So power, we know, is how fast energy is transferred. Okay, it's the speed at which you're using energy. If I had 100 joules of energy and I used it in 5 seconds, my power will be 100 divided by 5. If I had 100 joules of energy and I was able to use it all in 1 second, 100 divided by 1, that means it's more powerful because it can use the energy faster. Anything that's more powerful can use the energy faster. So the symbol we will just use P for power. The unit is watt, named after the scientist. This is the unit watt, W. The formula that we're using is energy over time. The amount of energy you use over a certain amount of time. That's power. So a 1 kilogram book is raised to a height of 9 meters in a time of 3 seconds. We need to find the power. The problem now is we don't actually have an energy yet. But let's have a look. We have a mass. We have a height. So I'm lifting up a height, which means there will be a gravity. So we will also have a G somewhere, 9.8, mgh. So the E that we're using could be the work done, potential energy, or kinetic energy. That's E work, E potential, energy, kinetic. It could be anything. In this case, mgh over T. So I'm going to just use 1 for the kilogram times 10. I know it should be 9.8, but let's just say 10 to keep it easy. Multiplied by 9, the height of 9, divided by the time of 3 seconds. This is my time. So putting that into your calculator, you should get 30 watts. So you can also find power with force. We know power is energy over time. Energy, work done, is force times distance. Remember, work is force times distance from the previous lesson. But now look at this part. What's this? D over T. That's V. D divided by T is V, so that's perfect. So instead of writing FD over T, I can simply write FV. So now if I have a speed and a force, I can also find the power. So those are two ways to find the power. We have PET, and then we have PFV. That didn't work very well. But anyway, so PET is PE over T. That's why I like to call it PET. And PE equals FV. So these are the two ways to find power. Here is another example. A force of 500 newtons is applied to push a crate across a floor of a speed of this. We have a friction. Find the power. P equals FV. No problem. P is 500 minus 100 multiplied by 2. Why minus? Because friction is always opposite of the motion, as we've discussed previously. So 500 minus 100. And then I'm going to multiply that by 2 meters per second. I will get 800 watts. So work and energy, we have the kinetic energy and work theorem. You will change your speed and you will do work to do that. So the net work is the change in kinetic energy. Of course, if I start pushing somebody faster, I will use some energy to do that, and he will be faster. He'll gain energy. So here is a work done. We have a starting speed. We have a final speed. We have a distance. The mass is obviously the same. It's the same block. The block is being pushed this way with a force of 2 newtons. If I wanted to find the initial kinetic energy and the final, we can do it. So that is EK equals a half mv squared. So what I'm going to do is I'll put that half multiplied by 2 multiplied by the starting speed here was 3 squared. Yes, half of 2 is 1 times 3 squared. 3 squared, 3 times 3 is 9. 1 times 9, of course, is 9 joules. Amazing. Final kinetic energy, we will do EK equals a half mv squared, but I'm going to do a half times 2, which is 1, multiplied by 5 squared. 5 squared. So that becomes 1 times 5 is 25. So we have 25 joules. Okay. Let's find the work done. Maybe we'll see some sort of pattern here. Work done, W equals FD. So FD, do we have it? Yes, we have a force of 2 and we have a distance of 8. So this is going to be my work. 2 times 8 is 16. Now, why am I doing all these calculations so soon? Well, let's find out. What did you notice between these two numbers and this number? That's 16, that's 25, that's 9. 25 minus 9 is 16. How cool is that? 25 minus 9 equals 16. This is the work energy theorem. I will take some energy to do the work, and that will be the increase over here. So from 9, I went to 25 because I did 16 joules of work. A bit of conservation of energy going on too. But anyway, work energy theorem. I will do 16 joules of work to increase his energy by 16 joules. So I will have to do final minus initial, right? So you'll calculate the final energy, calculate the starting energy, subtract them, and that will be your work done, like what we just did. Great. And what I've just explained, the net work, the overall work, is the final kinetic energy. Remember, it can be written as AK, KE. It doesn't really matter how you write it. It's just the same, okay? Final minus initial. Half mv squared minus a half mv squared, which is what we just did in the previous example. Here's another example to find the work done and the change in kinetic energy. So we have a force of 12 newtons. It makes a box move 5 meters. So we can assume the box was just standing and I've decided to move it 5 meters. To find the work done is force times distance, which is equal to 12 times 5, and that's 60 joules. And it says the change in kinetic energy. Well, the starting kinetic energy was 0. The final would have been 60. So you do 60 minus 0, which is 60 joules, essentially meaning the work done being 60, that is my kinetic energy of 60. Using that, I can do some other calculations. If I wanted to put this into the E equals a half mv squared, I can do that. If I know the mass, I can calculate the speed at the end as well.